Okay, so yesterday we started talking about improper integrals. And so recall these were these ones where you had infinite limits, right? You go from a to infinity or minus infinity to b. Today we're going to talk about another type of improper integrals, and these are the so-called type 2 improper integrals. So philosophically, this is really just the difference between looking at the chalkboard like this and like this. You know? It's just a matter of which way your head is turned. And what do I mean by that? Well, yesterday we looked at this sort of a graph. And we started at some point, say A, and then we said, does this graph decrease to 0 fast enough so that the area that you collect gets small fast enough that you actually, the amount of area you get converges to some finite value, right? That was our question. And we showed some examples like 1 over x squared from 1 to infinity where absolutely it does, right? It gets down fast enough. Now, there's another side to this picture that we didn't look at yesterday, and that's, well, you notice over here, this graph is going up towards infinity. Right? Maybe here I got a nice vertical asymptote. And instead of looking at the area under the curve from a to infinity, I might, let's say I need a letter before a. Z, okay, there we go. We just work around the alphabet. Z goes to a. So say that I had a vertical asymptote at z. I might ask, what's the area under the curve between z and a? Now, this never actually gets to the asymptote. So you're actually getting, as you get closer, you're still getting more and more area. But because the graph is getting closer to this line, you're getting less area as you get closer. And so you can ask again. It's the same thing. Is it getting close enough to z fast enough that the amount of area you get as you get closer to z converges to some finite value? And we're going to compute it in an analogous way. So now we're looking at this sort of area. And we're going to ask if this thing converges. So you see, it's really the same question. Just now, instead of converging towards something horizontal, you're converging towards something vertical. So the problem here, of course, the reason why we got a vertical asymptote is because we have some sort of discontinuity in the function. Right? So that's where these type 2 integrals are showing up, is when you have a discontinuity in your function. So for instance, right, if this, let's look at 1 over x, right? And let's integrate, say, from 0 to 1. That was just 1 over x. Okay. Now, when we wrote down the definition of the definite integral, we had an assumption, right? Namely, if you're integrating from a to b, then the function should be what? Continuous on the closed interval ab. This function, 1 over x, is not continuous on the closed interval 0, 1. Why not? It's not defined at 0. Right? You can't put 0 into here. If it's not defined, it can't even be continuous. It has to be defined in the first place. Okay? So this is not, well, a proper integral. Because 1 over x is not continuous, or even defined, on 0, 1. Right? So not find 0. Okay, that was the problem. Okay. So if we try to sketch a graph of 1 over x, so we'll stick 1 in here somewhere. Okay, so there's 1. So I'd like to compute this integral, okay, but I can't do it directly because this is not a proper integral. So I'm going to play the same game that we played yesterday. Instead of going all the way to 0, I'm going to stop somewhere. And let's call it, how about t? So I can compute this area. And if I do so, right, so what's going to be the area under the curve between t and 1? It's going to be the integral from t to 1, right, of dx over x. And now what am I going to want to do with this t? I want to move it towards 0, exactly. Okay, so I start moving it towards 0. And the closer I get to 0, the more area I pick up. Okay, so I can give actually a name to this function, g of t. Okay, so it picks up the area. And so I'm actually interested in the limit as t approaches what? 0, but there's more. The plus, exactly, right? I'm only approaching it from one side. Okay, I'm not approaching from both sides here. So I just approach 0 from the plus side. Okay. Okay, so that's what I'm interested in. And this is what I'm going to define as the area. Okay. Now, as usual, this limit doesn't have to exist. Right? It could be undefined, right? Do not exist. It could go to infinity. Right? But this is the definition we want to give. Okay, so this is, of course, equal to the limit as t approaches 0 from the right of the integral from t to 1 dx over x. And this is how we're going to define the integral from 0 to 1 of dx over x. Okay. If this exists, that's what we're going to define this integral to be. If this doesn't exist, then we say this doesn't exist, or we say it diverges. Okay. So in this case, we can actually do the computation. Okay, so we integrate from 1 to t. Oops, need our plus. Now let's see what happens here. We need an antiderivative for 1 over x. Okay, we did this yesterday, right? Remember, it's ln of x. Okay, and well, strictly speaking, it should be ln of absolute value of x. But since everything is positive, we don't worry about that. Okay, and then we have to evaluate at t and 1. So this is the limit as t goes to 0 of ln of 1 minus ln of t. Okay, now let's see. ln of 1 we saw was 0. So this is just minus ln of t. Okay, now what happens to ln of t as t goes to 0? Let's see. Let's draw our graph. Right. So this is ln of x. So as x goes to 0, it goes to negative infinity. So this is just going to go to minus negative infinity, right? So this is going to infinity. Okay, so this limit doesn't exist strictly. It's going to diverge. So this one, you're actually going to get infinite area, right? But remember yesterday when we had 1 over x and we went 1 to infinity, we weren't surprised. I mean, we got infinite area also. So maybe this isn't too surprising. Okay, so this is just infinity. Okay, so this says that this integral diverges. Okay, goes to infinity. Okay, well, maybe you're not so surprised again. You know, well, geez, you know, it goes up to infinity. It never gets to where it should be going. Infinite area. I mean, I'm not surprised. Okay, so let's see one that actually does converge. Okay, so let's look at this ln of x. So let's see, at 1, that's when it gets to 0 here. And why don't we see what kind of area you have in between? Right? Let's see if it does any better. So let's integrate from 0 to 1 ln of x. Okay, so we're going to get this. We're going to try to get this area. See if it's any better. Maybe it is. Maybe it's not. Okay. Well, again, this doesn't make sense as a proper integral, right? Because ln of x is not defined at 0, so it's not continuous at 0. So we can't just evaluate this directly. Okay. So we have to use, right, this limit definition. The limit now is t goes to 0 from the right. Whoops, forgot our integral. Integral from not 0, but now t, ln of x dx. Yep. Everybody agree that that's the right thing to look at? Okay. Again, what does this mean? It means instead of going all the way to 0, I stop at some t. Okay, and I just compute that area, and then I take the limit as t goes to 0. Okay. Now to compute this, I need to know the integral of ln of x. Anybody remember that? Or at least remember how to do it? Let's see, we'll do a little side work here. Integral, we just need the antiderivative, right? Antiderivative ln of x dx. Close. How do we get it? Because we've got to know how to check anyway. So. Integration by parts, right? Okay, so let's use the tabular method. ln of x and 1. Derivative ln of x is 1 over x. Antiderivative of x is x. Then we can move this 1 over x over. When you move it over, it's cool. This becomes a 1. And this moved over, so it becomes a 1. And then when you differentiate, you get 0. And when you anti-differentiate, you get x. You get plus, minus. So x ln of x minus x. Let's see. Okay. Cool. So this is equal to the limit as t goes to 0 from the right of x ln of x minus x plus, well, we don't need plus c, do we? Evaluated at t and 1. Okay. So this is the limit as t goes to 0 from the right of, okay, so first we evaluate at 1. Now when I evaluate at 1, what happens here? Well, I get an ln of 1 here. What's ln of 1? That's 0, so that term goes away. And then I just get a minus 1. Okay. Then I have to subtract what happens when I evaluate at t. And when I evaluate at t, I get t ln of t minus t. Okay. So what happens to this expression as t goes to 0? the t part goes to 0. The ln of t part goes to minus infinity. Oh. Then we subtract something which goes to 0, so we don't have to worry about that. Whatever that is, that's not going to be too important, right? That's the important bit. So what was the limit as t went to 0 of t times ln of t? So if something going to 0, that should be making it, when you multiply something, it's going to 0, it should be going to 0. On the other hand, that's going to minus infinity. So the whole thing should be going to minus infinity. Remember yesterday we talked about this problem, right? You can't infinity, minus infinity, all of a sudden you had a problem, right? And now we can really see it happening, right? Where should this go? Right? Okay, so last term we actually figured out how to answer these questions. Something called L'Hopital's rule. But let's remember the general rule, which is this. Exponential functions grow the fastest, then polynomial functions, then logarithmic functions. Okay? So when they're battling against each other, you look and see where they are in that list. Okay? If it's a logarithmic function, that is kind of the weakest. It's like rock, paper, scissors, but nothing beats rock. Okay? That's the exponential function, that's rock, but nothing beats rock. Okay? So the exponential function will always win out over polynomials or logarithms. The polynomials will lose to exponentials, but will beat logarithms. And logarithms lose to everybody. Okay? That's how the race goes. So since t is a polynomial, it beats logarithms. So it's going to go to 0. Okay? But let's just write this out with L'Hopital's rule. Just check this. So L'Hopital's rule doesn't apply directly in this case. It looks at infinity over infinity or 0 over 0. So the way that I fix this is by what? Well, I can write this as, say, ln of t over 1 over t. T squared over t, that would also be true, although it probably complicates matters more than simplifies them. Yeah. Another way to write this, of course, would also be t to the minus 1, right? Remember, if you allow yourself to negate exponents, you can move things up and down at will. So that's a t to the 1, so to put it under, you get t to the minus 1. Okay. Well, now as t goes to 0, t to the minus 1 goes to infinity. Okay. So that's going to, well, that goes to minus infinity, but we don't worry if it's minus. That goes to infinity. So L'Hopital's rule applies, which means you get the same limit if you differentiate the top and the bottom. The derivative of ln of t is 1 over t, right, or t to the minus 1. The derivative of t to the minus 1 is minus t to the minus 2. Now, well, I don't worry about this minus. I'll just pull that out. And I can move this t to the minus 2 back up and make it a t to the 2. But when I do t to the 2 times t to the minus 1, I get t to the 1. So I just get t. And this goes to 0 now. So you can use L'Hopital's rule on this. Or just use the general rule, which is that exponentials beat polynomials, polynomials beat logarithms. Okay. So this bit goes to 0, and this bit goes to 0. So you're just getting minus 1 minus 0, which is minus 1. So the area, where I use the term area loosely here, right, allowing for things like negative area, under or between the curve ln of x, the line y equals 0, and under the x-axis is minus 1. So that is, if you move this t over, the area you get converges to minus 1. So that's maybe a bit surprising now. But it works. Although it shouldn't be as surprising after the type 1 integrals worked out. Okay. Now, perhaps we should just write down the general statement then. And then we need the other side. So let's let f of x be continuous on the interval a to b, or I don't include a. So before I was always including a, but now I don't. We define the integral from a to b of f of x dx to equal the limit as t approaches a from the right of integral from t to a, t to b of f of x dx. Okay, so that's our general definition. Okay, and that's how we handle a problem on the left side. Now, I'll just write it down, and you won't be surprised. If f of x is continuous from a to b, and now you don't include b. So now the problem is on the right side of your interval. Okay, for instance, if you were doing 1 over x, but you were looking at the negatives, right? Say you wanted to go from minus 1 to 0. Well, now the continuity problem is on top at the 0. Then we can define the integral again from a to b of f of x to be, well, now the limit should be as t approaches b, and not from the right, but from the left, right? Because it's approaching it from below. Integral from a to t f of x dx. Okay, so that's our second one. And then the third one is, well, this is what happens quite often, is you want to integrate over some interval, and in the middle of the interval is a discontinuity. Right? For instance, let's say I wanted to integrate 1 over x from minus 1 to 1. If I did that, my endpoints are not problems, but there's a 0 right in the middle. That is a problem. So if, say f of x is continuous on the interval ab, except at some c, which is somewhere in the middle, say not one of the endpoints. So it's continuous at every single point except one. Then the integral from a to b of f of x dx, well, we just break it up into two integrals. Okay, this is very similar to what we did when we wanted to integrate from minus infinity to infinity. All right, we break it up into two integrals, one that goes from minus infinity to a, and the other from a to infinity. So here, we integrate from a to c. C is this discontinuity. And then we integrate from c to b. And the reason we do this is now, each of these is again an improper integral. Right? Because the function is not continuous at c. Right? But now we can revert back to these two definitions. Let's see, I guess I wanted to do one more example. Depends what time is it. Okay. All right, so let's do another example. So let's integrate from 2 to 5. We'll do the integral of dx over the square root of x minus 2. Yeah. Okay. So is this a proper integral? Why not? It's 2 is, it's not continuous at 2. It's right. It's not even defined at 2, the function, right? Okay. So I can't, it's an improper integral, so I'm going to have to just approach 2. Okay. So this is going to be the limit as t approaches 2 from the right. Integral t to 5 dx over the square root of x minus 2. Okay, so now I need an antiderivative. Let's start easier. How about a U sub? Yeah. We don't need to whip out the trig substitution. You keep that to yourself. Oh dear, that sounds kind of dirty. All right, so yeah, let's see. What would my U substitution be? Oh, okay, that's nice, right? So then dx is just du, right? Okay, so this is really cool, right? You could actually just, this is the same problem as if you had du over the square root of u. Okay. Okay, of course we have to worry about our limits, but we'll just substitute back at the end so we don't change our limits. Okay, so du over u, over the square root of u, what's the antiderivative of that? Let's see. If you wanted to integrate du over the square root of u. Yeah, let's see. Well, this is u to the minus 1/2 power, right? Yeah, right? You add 1 to the minus 1/2, and you get a half. 1 over a half is 2. And then u to the 1/2, and then, of course, we have plus c. Okay. And then in the end, right, we want to replace our u back with x minus 2. Okay. So this is going to be the limit as t goes to 2 from the right of, all right, so we get 2 square root, because it's 1/2 power, x minus 2. We don't need the plus c, and then we evaluate at t and at 5. Okay. So now this equals limit as t goes to 2 of, all right, we have to put in the 5. So when you put in a 5, you get 5 minus 2 is 3. So 2 root 3 minus, when you put in a t, well, you just get 2 square root of t minus 2. And as t goes to 2 from the right, this just approaches 0. So this whole thing goes away, and you just get 2 root 3. Now, something sort of weird happened here. Our original function was not defined at 2. It wasn't continuous because it wasn't even defined at 2. But the antiderivative that we got, it is defined at 2. You can just plug 2 right into the thing. Right? If we'd have had a 2 here, we could have just plugged it right in and gotten 0 right off the bat. We wouldn't have had to take any limit at all. That's a little peculiar. Right? So actually a more general thing is happening, and I want to use it to motivate something called the generalized antiderivative, which is somewhat of a shortcut on these type 2 improper integral problems. So I want to show you something called a generalized antiderivative. It looks like an antiderivative, only it's slightly more general. Okay, so let's let f of x be continuous on the open interval AB. Okay. Now, I'm not going to give you the most general definition of a generalized antiderivative, but this will be good enough for our purposes. Okay, so let's let f of x be continuous, but it's not on the closed interval, okay, just on the open interval. I guess it shouldn't be capitalized. A generalized antiderivative of f of x on AB, the closed interval AB, is a continuous, well, I should say, is a function capital F of x continuous on the closed interval AB such that, well, if it's an antiderivative, it should be that the derivative of f should equal little f, right, on the open interval. Right? We can't say any more than the open interval because this function may not be defined on more than the open interval. So this is just a slight difference between the normal definition of an antiderivative and this generalized version of an antiderivative. Namely, this antiderivative is defined at more places, right? Namely, the endpoints of this interval. Okay, and that's just the only subtle difference. Okay, so it doesn't seem like you're adding a whole lot. Okay? But the upshot is that we get the following. And this requires a proof, but we won't give it. If f of x is continuous on the open interval AB, and capital F of x is an generalized, is a generalized, antiderivative should say of f of x on the closed interval AB, then we can actually integrate f of x from a to b. Right? Even though normally we wanted, if we wanted this to make sense, we would need that f of x is continuous on the closed interval ab. Right? That's what we've always said. But here it's not continuous at either of the endpoints. But if we have a generalized antiderivative, then we can actually evaluate it, and it's exactly what the fundamental theorem tells us it should be. You can evaluate the antiderivatives at the endpoints. So, if we go back to our example here, this is continuous on the interval 2 to 5, but not including 2. Right? But it has a generalized antiderivative on the closed interval 2, 5. Right? What's the generalized antiderivative? Well, it's 2 square root of x minus 2. Right? This is an antiderivative for that function, but it's actually continuous all the way from 2 to 5. It doesn't have a problem at 2. And so what that tells us is that this is equal to 2 times the square root of x minus 2 evaluated at 2 and 5. Okay? You don't need to worry about limits in this. Okay? Now, when we did this for 1 over x, we couldn't play this game because the antiderivative was minus, the antiderivative was ln of x, which is also not defined at 0. So it's not a generalized antiderivative. Right? It's not, ln of x isn't defined at 0. So we couldn't play this game. But here we can play the game. Okay, so this is kind of a shortcut on some of these. I don't think this is usually taught anymore. But so you may not have seen this if you took calculus before. But it's true. Well, let me do another example of that. Would that be helpful? Yeah, let me do another example. This one will be a little more complicated, but only because I want you guys to have some more fun with integrals. I don't want you to forget how to do them. 100 on the problem set was not enough. All right, so this one requires me to write it down after looking. So we're going to integrate minus 3 to 3 x squared dx over the square root of 9 minus x squared. Okay, so this idea of a generalized antiderivative suggests a strategy for solving these problems. Namely, first compute the antiderivative, forgetting about the limits. Okay, just do the as if it was an indefinite integral. Okay? Now, we should point out, right? Okay, minus 3 causes a problem here. So does 3. 3 causes a problem as well. If we followed, I guess it was the third one on here, right, that would tell you have to break this up as, you're going to have to break it up actually into. Actually, the way we wrote it down in the third one doesn't tell you that, but what you should do is, right, pick some point in the middle and break it up into 2 different integrals, okay, and then you can take limits on both of them. Okay, that's what you have to do. Okay, but instead of doing that, let's first find the antiderivative, and if we're lucky, it will be defined at both minus 3 and 3. Yeah? A middle point. So then you have to break, that's what this third one said, is you have to break it up at the point where you have a discontinuity. Yeah, so, okay, so what Dina's worried about is this, right? You have, say, an interval A, C, B. And say the function has problems at A, C, and B. You're wondering, right, how do I break up my integral? Right? And here's what you're going to have to do. This is really nasty, and you're not going to like me for it. Okay? But assuming that you can't play any tricks with the generalized antiderivative, because that solves a lot of problems, you're going to choose a point in the middle between A and C and between C and B. Okay? So let's call this one D1 and D2. Okay. And now you're going to integrate from A to D1. Okay. And now you only have one problem. Okay, the one on at the A. Then you're going to integrate from D1 to C. And again, now you only have one problem, the problem at the C. And then you're going to integrate from C to D2. And again, you only have one problem, the problem at the C. And then there should be F's here. And then lastly, you'll integrate from D2 to B. And again, you only have the one problem, the problem at the B. Okay, so that's how you'd have to do it. You have to break this up into 1, 2, 3, 4 integrals. That's why I say you're not going to like me very much. Okay, so just hope I don't give you an interval where there's a lot of discontinuities. But if you don't worry about the computational complexity, right, you can say at least what you have to do. You always want to break it up so that you only have one discontinuity and it's on an endpoint. Okay, that's how you always want to break things up. Jenna, you look like that's not very clear.
No, I didn't.
Do you? You're okay? Okay. All right. Well, to evaluate this, let's first evaluate the related but simpler problem. This. Okay. Okay, so have at it, my integral experts. You want to try trig substitution? Okay, so what would be the trig substitution? A sine theta, is it quite done? What's the A? Okay, so A is 3. Yeah. Okay, so then dx would be 3 cosine theta. And square root of 9 minus x squared, right, would be 3 cosine theta, right? Okay, cool. So then this thing becomes, yeah, I figured from there we could probably get it. But I mean, yeah, strictly speaking, we could write it. X squared equals 9 sine squared theta. Yeah. Okay, so x squared becomes 9 sine squared theta. Dx is 3 cosine theta. And square root of 9 minus x squared is 3 cosine theta. Oh, I forgot a d theta here. Okay. So the cosine of thetas cancel. The 3's cancel. The 9 will come out. And so I'm just left with computing the integral of sine squared. Right? And that we've done before several times. So let's see, this is equal to 9 times the integral of sine squared theta d theta. So either you remember the formula, in which case I hate you, or you can recompute it. So let's see. You remember what method we used to integrate that? By parts, yeah? Okay, so you do sine theta, sine theta. So you differentiate and you integrate. And then you play the trick where you move this cosine over. So that becomes a 1. This becomes a minus cosine squared. And then you play another trick. Cosine squared is if you forget about the minus, that makes it hard to remember, right? It's 1 minus sine squared, so then this will make it sine squared minus 1. Right, just swaps the order. Okay, so this is actually equal to, now I feel like there's a problem with our, I don't know why I feel like it should be, this should have been minus or not minus, but I mean, I guess it's okay. Ah, well, okay, well, yeah, it won't matter. Yeah, normally I move that minus over, that's why. Okay, that's fine. So now we differentiate, and that becomes 0. And, well, our original integral, if we call this bit I, well, when we anti-differentiate, right, we're getting I again for this part. And then that becomes minus theta. So this becomes I minus theta. So then we're done because we're at 0 here. So you get minus sine cosine, and then, let's see, this is plus and that's minus. Minus I minus theta. Okay. Minus I, yeah, minus I plus theta. So what did this become? It becomes, okay, well, you got your 9. And now, well, remember how it's going to work. I is going to equal minus sine cosine plus theta minus I. You add the I to the other side. That gives you 2 i's. You divide by 2. Now you get a half. So that'll give you a 9 halves. Right? You have a plus theta and then a minus sine cosine. Okay. Now, It's not quite nice because we have it in theta, but it would be nice to have it in x's. So let's shoot up here. Okay, we got to snake it up here. So let's see. The 9/2, that's not a problem. Now theta. So let's see. If x is 3 sine of theta, then to get theta, okay, I divide by 3 and then take the arc sine. Right, so this becomes arc sine of x over 3. Okay, now let's see, minus sine of theta, cosine of theta. Well, the minus I can do. Sine of theta is x over 3. Right, because x is 3 sine theta, divide by 3. Okay, that's easy, x over 3. Now I need cosine of theta. Okay, so how did I do this? How did I work this out? Do a little triangle, right? You could also use Pythagorean theorem, but use this formula that 1 equals sine squared plus cosine squared, but let's just do it like this. Okay, so we know that the sine of theta is x over 3. Right, so if that's your theta, the sine, the opposite over the hypotenuse, is x over 3. So then the last side is the square root of 9 minus x squared. So the cosine is square root of 9 minus x squared over 3. So this is times the square root of 9 minus x squared over 3. Okay, and then, of course, we plus c. And I guess there should be a plus c down here, too. Okay, and so, well, let's see. That's going to give you an over 9. And that'll actually cancel with that 9, so that's kind of cool. So if I move this all in, I get a half, or 9/2 rather, arc sine of x over 3 minus x square root of 9 minus x squared over 2 plus c. Okay, and that's looks nasty, but it's an answer, right? Okay, that's our integral. Okay, now, what's really cool about this integral? Well, I can put arc sine of, I can put any real number into here. It's not going to break the function. Okay, and same thing over here. I can put anything in for x, and as long as x isn't bigger than 3 or less than minus 3, I can put anything in here. Okay, and since in the end I just want to integrate between minus 3 and 3, nothing outside of that, this function is continuous, not just from minus 3 to 3 with parentheses, but from minus 3 to 3 with brackets. Which means it's a, say it louder, generalized antiderivative. Yeah? Okay? It's not just continuous on the open interval, it's continuous on the closed interval, right? Closed, meaning it contains the endpoints. Okay, so this is a generalized antiderivative for x squared over the square root of 9 minus x squared on minus 3, 3. Okay? Which means that I don't have to evaluate this with limits at all. I can actually just write down the generalized antiderivative evaluated at the 2 endpoints. So this equals, well, let's see, we've got to write down our business here. 9/2 arc sine x over 3 minus x square root of 9 minus x squared over 2 evaluated at minus 3 and 3. Right? We don't have to deal with the limits at all. So this is very nice. This is a nice little shortcut. Okay, so, well, let's see if we can't figure it out. If I put in a 3, then, or a minus 3, this part is always going to go to 0. Right? Because the 9 minus x squared is just going to become 9 minus 9, which is 0. So this term's never going to be relevant. That's nice. So actually, this is the only part that's relevant. So I'm just going to get 9/2 arc sine of, well, 3 over 3 is 1, minus 9/2 arc sine of minus 3 over 3 is minus 1. Okay, so what's the arc sine of 1? We'll see. So it's asking when is the sine function 1? All right, up at pi over 2. And when is the sine function minus 1? 3 pi over 2, or, well, the way we define things, negative pi over 2. So you get pi over 2, forget about the 9/2, minus negative pi over 2. And we'll factor the 9/2 out. So 9/2 pi over 2 plus pi over 2, which is just pi. So 9/2 pi, or 9 pi over 2. This is very nice that such a nasty problem could actually have such a simple answer. And you'd have to write any limits down. I mean, you would have to do this business anyway, right? Because you need the antiderivative. But not having to write down the limits at the end, this is priceless. Okay. Any questions about this? Okay. So if as you're going through problems and you see these type 2, always remember, find the antiderivative first. Right? And check if it has the same continuity problems as your original function. And if it doesn't, then you can use the fundamental theorem as usual. This is very nice. But mention that you're doing it. Say, this is a generalized antiderivative. That at least gives some justification. It shows that you actually know what's going on. Okay, so the next thing that I need to show you is called the comparison test. And this is very difficult to apply well over a long... If I give you a lot of problems, you could spend a lot of time using it. And I did give you a lot of problems, and you will spend a lot of time using it. But the principle, I think, is incredibly easy. So all it's saying is the following. Let's say I want to know whether my integral converges. Okay? So I know that over this infinite, say we're looking at one that goes from 0 to infinity. Okay? And I want to know whether or not the area bounded is finite. Okay? And let's say that I know that it is smaller, my function is smaller than some bigger function. And that I know that that bigger function converges. So it contains more area, but still finite. What can I say about my original function? Does it converge? Right? This bigger function converges, and I want to know about the smaller function. Is it possible that you could have a big function which converges and a small function that does not? It's not a trick question. No. All right? I mean, think about it. Draw a little picture here. Okay. I get a nice little function. Okay, so call that my function g. Then I have another function up here, all right, which is always bigger than g. Okay, that's my f. Okay, so here g is always less than or equal to f. Okay, so I get more area. Okay, and assume that, say, from 0 to infinity, this thing converges. What can I conclude about the integral from 0 to infinity of g? It's got to converge, right? If something has less area than something which has finite area, then it must also have finite area. Yeah? This is reasonably clear, I think. So we're only dealing here with, we're talking about area, we're talking about positive functions, okay, where we know that one of them is always less than or equal to the other. So for every value, g of x is less than or equal to f of x. Okay. That's it. That's one. I mean, that's the first half of the comparison test. What's the other half of the comparison test? The other half, well, it's actually the same picture. Okay, and this 0 here is irrelevant. I'm just using it for something. Okay. Let's say instead, I do this backwards, though. Instead of knowing that f converges between 0 and infinity and wanting to show that g converges, let's say I want to know something about f, and all I know is something about g. Okay? Let's say I know that the integral from 0 to infinity of g diverges. Okay? So there's an infinite amount of area under g already. And now I take a function which is bigger, f. What can I say about that integral? It's got to diverge, right? If you have more area than something which has infinite area, then you must also have infinite area, right? Okay, so this implies the integral from 0 to infinity of f dx diverges. It's simple. Okay, and you can see why they call it the comparison test. You want to show that something converges or diverges by comparing it to something else that you know. Okay? Now, I said earlier, not earlier today, but earlier yesterday or the day before, that we wanted to know certain things like, remember we computed this, right? We decided when this would converge or diverge, right? We showed that this, right, converges to, well, diverges when p is what? It diverges when it was less than or equal to 1. And it converged when p was greater than 1. And it converged actually to 1 over p minus 1. We did show this, didn't we? Oh, maybe in the other class I did, and maybe I didn't do it in here. Oh, dear. Oh, dear. A little bifurcation. One class I got a little further yesterday. I did. Ah, yes, I'm sorry. Okay, exercise. Oh, dear. Yes, okay. That's right. I was supposed to start with this. I forgot. Ay, ay, ay. Very bad, very bad. Okay, this is called the p-test. Oh, dear. All right, this is very easy to show. Okay, and you should do so, right? You just have to, well, it's an improper integral. Right? You have to take the limit as t goes to infinity of the integral from 1 to t of dx over x to the p. Right? And then you have to find an antiderivative, which is very easy. You know how to do this, just the power rule. Right? And then you just need to see what happens in these two cases. And you'll see what happens. When p is less than or equal to 1, you get something which is just t to the p, or t to the minus p. And so it ends up going to infinity. And then when p is greater than 1, it just becomes this. You work it out. It really will take you less than 10 minutes. Very easy. Okay, well, assuming that you've done so, I won't have this problem this afternoon. Assuming that you've done so, you now have a nice class of functions to compare things to. Okay. So let's see. Do I have a nice? I think I had a nice example. Yeah. So let's look at 1 to infinity. I'm going to change up my example now. Okay. Let's try to look at this nice integral. Are you laughing at me, Chris? Oh, no, you're laughing with me. Ah, yes. Okay. Now, I don't actually want to compute this. I just want to know whether it converges or diverges. Okay? Whether it has a finite value or not. Okay. So I want to use the comparison test. So I need to compare it to something that I know. Okay. Now, I have down here, I see this nice x squared, right, which would be a special case here of x to the p when p is 2, which is in the p greater than 1 case, where it does converge. Right? So if I could show that this function was always, on this interval anyways, less than or equal to 1 over x squared, then I'd be done, because I could compare it, right, using the comparison test. Okay, well, let's take a look. what do I know? I want to compare cosine squared x over x squared with 1 over x squared. Now, when, well, I should just say we're on the interval 1 to infinity. Okay. Whether it matters or not, that's where we are. What do I know about cosine squared? What values does it take? What about cosine? -1 to 1. Okay. So if I square those values, all the values between -1 and 1, then I get values between 1 and 0, right? 0 and 1, right? So, of course, all the negative stuff becomes positive when you square it. You still have a 0, because when you square a 0, you get 0. You still have a 1. Nothing can get bigger than 1 when you square it. Right? So it's all the stuff between 0 and 1. So we know that cosine squared x lives in between 0 and 1. So that means, well, if I have a fraction, and if I replaced every numerator with 1, which is bigger or equal to what cosine squared of x is, what happens to a fraction if I replace the numerator with something bigger? The fraction gets bigger, right? So that tells me that cosine squared of x over x squared is always less than or equal to 1 over x squared. Right? If I take a fraction and I increase the numerator, then I make the fraction bigger. Okay? And this holds for all x. In particular, it holds for all x between 1 and infinity. Okay? These things are all positive. So it satisfies the case. Right? I have two functions. Okay? I have this function cosine squared x over x squared. I have the function 1 over x squared. Right? This function is always greater than or equal to 0. This function is always less than or equal to 1 over x squared. And so, by the comparison test, if I integrate, well, here I wrote 0, but the 0 is irrelevant. If I integrate from 1 to infinity, 1 over x squared, well, the p-test tells you that that converges. In fact, it converges to 1 over 2 minus 1, which is 1. Okay? But it doesn't matter. It converges. And that implies that the middle one converges. So since the integral from 1 to infinity dx over x squared converges, right, by the p-test, this implies that the integral from 1 to infinity of cosine squared x over x squared dx converges. Right? And this implication, right, this is the comparison test. Okay. Y'all. Yeah. Questions about that? The hard part about this is not understanding the comparison test itself. It's you start with some function, and you now have to find a function to compare it to. That's the trick. This is always going to be the tricky part. So maybe I'll just quickly write down something. Another one. It's actually very related to this first one. Let's say we were integrating, again, 1 to infinity. And now we'll do x plus sine squared x on the bottom. So you're interested in comparing this function 1 over x plus sine squared x. Now, whenever you get these sines and cosines, it's important to remember, right, they're defined, their range is always going to be between -1 and 1. That can be very useful. Okay. Sine squared, of course, will go between 0 and 1. Now, if I replace sine squared with the biggest that it gets, which is 1, then it will make the denominator bigger, which will make the fraction smaller. Okay, so that's a way I could compare it to something, to what? Well, if I replace, how do I compare these two things? X plus sine squared x and 1 over x plus 1. Right? Which one is bigger? Right? This is going to be, generally speaking, bigger, right? Because, remember, sine squared is not always, but usually less than 1. When it's less than 1, the denominator is smaller, which makes the whole fraction bigger. So this is normally bigger than 1 over x plus 1. Okay? They become equal if sine squared equals 1. Okay? So if you could show that this diverged, then you would know that this diverged, because it's bigger. Now you might say, well, why don't I use, instead of making sine squared big as possible, making it 1, why don't I make it as small as possible, make it a 0? Okay. Well, if I make it as small as possible, then it becomes 1 over x. So then you'd be saying, if I can just show this converges, then this will converge. But 1 over x, right, that diverges. That's part of the p-test. Okay, when p equals 1, when you have 1 over x, it diverges. So that won't be useful to show it converges. So if this did converge, which it won't, but if it did, this would not be a good thing to compare it to. Okay? You can see why this is tricky, it's a little challenging. Is because you have to find the right function, figure out, I mean, right from the start you have to decide, well, do I want to show it converges or diverges? So you have to start getting a feeling for it. And the only way you can get that feeling is to do a lot of problems. Okay, so this is the one to compare it to, and this is actually, it's pretty easy to see that this thing is going to diverge, because it's really the same thing as 1 over x. Right? You've just shifted the graph over by 1 unit. But if you have something which has infinite area and you shift it over by 1 unit, I mean, you're still going to have infinite area, right? You can't change that. So this thing will diverge, right? And since that's bigger than it, it'll imply that one will diverge. Okay. So this takes a little bit of practice and a lot of creativity sometimes. So, okay.